Hey everyone, today's lesson will be the last lesson or last portion of the Similarity of Figures unit, and we're going to be looking at similar triangles. Now, when we're talking about triangles, the sum of all angles of a triangle is always 180 degrees. So when you add up the three different angles of a triangle, it will always add up to 180 degrees. If two corresponding angles in the two triangles are equal, the third angle will always be equal. So that's saying if you had two different triangles and two of the angles are the exact same in both of the triangles, that means that third angle is also going to be equal. Two triangles are similar if any two of the three corresponding angles are congruent, or one pair of corresponding angles is congruent and the corresponding sides adjacent to the angles are proportional. Two right triangles are similar if one pair of corresponding acute angles is congruent. Now, given the two triangles below, find the length of n. So we're trying to find the length of n on the bottom here. And we're given a, on this side, we're given the length of this one here, and the length on the bottom. If you know that two of the three corresponding angles are congruent, so angle C up here is equal to angle N, this means that triangle ABC is similar to triangle LMN. So if we have angle C and we know that they match up and two of the three corresponding angles are congruent, then we can solve for N. Now we're going to set up a proportion here with our matching sides. If we think about our smaller triangle here being our scale, and this being our original, we can match up our sides. So we have this length right here, which is 2 inches, and that would be MN over our corresponding side with that would be BC. So we'd have our scale over our original, which is 2 over 5. This corresponds with, well, if we're looking for our bottom here, so we're trying to find out where n is. Let's clean that up a little bit. We're trying to find out this line here where n is, and we know C across the bottom here is 7. Well, we can do n over 7. This will allow us to do our cross multiplication and solve for our unknown value, which is n. Take this further, we get 5n equals 2 multiplied by 7. Then we have 5n equals 2 times 7, which is 14. Get n by itself by dividing by 5. Divide by 5. It cancels on the left-hand side. And we're left with n equals 14 divided by 5. And this will equal 2.8 inches. So our bottom portion for n would be 2.8 inches. And that would be our final answer. And that would allow us to use our known values for the original triangle and our one known value on our scale triangle to solve for that one unknown value on the bottom of that triangle. Now we can try this out by finding the length for x. The two triangles are similar. So right away it's telling us that these triangles are similar. We have a value from A to B, which is 6.1. We have a value from B to C, which is 5.3. And we also have a value from y to x on our scale, which is going to be 4.5 centimeters. Now, y and x, so this line here, would correspond with this line right here, AB, if we rotate that triangle. So if we rotated this, it would match up with that line there. So what we can do now is set up our proportion where we have 4.5 over top of 6.1, because that's the side that it corresponds with. And then we have our unknown x over top of our 5.3. Now we have our cross multiplication that we can cross here. And this is going to give us 6.1x is equal to 4.5 multiplied by 5.3. If I move down here, we have 6.1x is equal to 23.85. Now we have to get x by itself, so we divide by 6.1, divide by 6.1, cancels off on the left-hand side, and we get x equaling 3.9 centimeters. And that would be our unknown value for x. So this would be 3.9 centimeters, and that would be our final answer for this part. Now for this shape here, we have, are the two triangles ABC and EDC similar? They give us AB, which is 4, BC, which is 5, and AC, which is 6. DC equals 2.5, and last EC equals 3. So what we have here is a triangle within a triangle. Now, to make this easier to understand, I'm going to break these apart so you can truly look at the different dimensions and the lengths that we're given. So I'm going to make one triangle here, which will be our bigger triangle, and another one here, which will be our smaller triangle. Important thing to note here is I didn't draw these triangles to scale. I just drew them so that we can get a rough idea of what the triangles will look like. So we'd have our bigger triangle, which has 6, 4, and 5, because we have A, B, and C. And then we have E, D, and C again. And we know that DC is 2.5, and we know that EC is 3. So what we're trying to figure out is, are these similar triangles? The way that we'd go about figuring this out is figuring out if the scale factors are the same. The way we're going to do this is compare the same parts of the triangle. So we're going to compare the hypotenuse by the hypotenuse, or the bottom of the triangle with the bottom of the triangle, or the left side with the left. The only problem is we don't know what that left side is, so we can only compare the hypotenuse and the bottom of the triangle. If we have the smaller one on top, which we could call our scale and our original, we have 3 over 6, which gives you 0.5. So our scale factor is 0.5 for this portion. We're hoping that the other portion is also 0.5 so that we know that it is similar. If it is a different value, the triangles would not be similar. Now we have 2.5 over 5, which gives us 0.5, meaning that yes, the triangles are similar. So our scale factor would be 0.5 for both of them, meaning that the triangles are similar. Our last question here has Roberto and Marcos tie wires to either side of an artificial tree as part of the setup of a concert stage. They decide to attach the wires so that they both make 35-degree angles within the triangle. Are the right triangles created by the wires similar triangles? what they did here is they created a 35 here and a 35 here. The 90-degree angle is created where the tree starts to rise up with the floor. So we have a 90-degree here and a 90-degree here. What we want to know is this top angle the same on both of the triangles so that we can determine if these triangles are similar? Well, the first thing that we should think about is on the last page, we talked about if you know two angles within one triangle that are similar to the other triangle, you know that those triangles are going to be similar. But to make sure, what we can do here is 180, subtract 90, subtract 35. So we're subtracting the two angles we know, and we want to figure out that top angle because all triangles add up to 180 degrees. So we have 180, subtract 90, subtract 35, leaving us with our top angle of 55 degrees. We'd do the exact same thing on the other triangle if we wanted to make sure, and this would tell us that it is as well 55 degrees. So this angle at the top is 55, helps if I write the correct number, 55 and 55. So we know that these two triangles are going to be similar because the three angles are equal. This will finish off our lesson for this unit and complete this unit lessons. And what you need to do now is make sure you are letting me know on if you're going to be completing a project for this unit or if you are going to be writing the test. Other than that, make sure that you have a good day, and if you have any questions, send me a message on Teams or you can ask me in class.